Good morning, good afternoon, good evening, as the case may be. I am Madan Rehani, President, IOMP. I welcome you to this IOMP webinar. Thanks to all of you for participating in this activity. Today's webinar is going to be on proton shielding, and I will be introducing the moderator of the webinar, who is Dr. Geoffrey Ibbott. He is chair of our science committee of IOMP. For many years, he was the chair of the Department of Radiation Physics at the Anderson Cancer Center in Houston. He has been involved in variety of activities at the national and international level. He was president of AAPM. He has been involved with UNSCARE, and he says that he is retired, but he's very active all over and is currently now the Associate Executive Director for Physics at the American Board of Radiology. He is also consultant in medical physics. So with these few words, I will pass on to Dr. Geoffrey Ibbott to start the session. He will introduce the speakers. Just before I pass on to him, two announcements, because we often find question in the chat box. So on making the webinar available on the website, yes, the webinar is going to be recorded, and within 48 hours, we normally place them on the IOMP website. IOMP does not give certificate for participation or any CME. The webinar is of 60 minutes duration, and at the end of it, we will announce the next webinar, which is on 6th of October. With that, I will pass on to Professor Ibbott to introduce the speaker. Jeff, please.
Thank you, Madan. And it's a pleasure to be with all of you today. I know that the hour is very early in some places and very late in others. So we're all very grateful that you've been able to join us for this webinar today. And this is a very interesting topic. This topic was requested by participants in previous webinars. And today, as you see, we're talking about proton facility shielding. And we're going to talk about both the regulatory issues and aspects of design of proton shielding. And we have two very highly qualified speakers today. Our first speaker is going to be Dr. Katja Langen. Dr. Langen is professor and associate director of medical physics at Emory University, which is in Atlanta in the US. Dr. Langen began her career with a degree in health physics from a German institution, and then received a master's and a PhD in medical physics from the University of Wisconsin. She did both a clinical residency and then a postdoctoral fellowship, and then moved to a position at another MD Anderson Cancer Center facility, this one in Florida, where she was put in charge of planning the proton facility that they ultimately did build there. She spent some time at the University of Maryland, where she directed the physics group at the Proton Center there, and has now moved, as I said, to Emory University and is responsible for their proton facility. And as you see on the screen, one of her many publications and other works has been to help write an IAEA document on developing a proton facility. And then our second speaker is Dr. Nissi Ibbott, who is based in California and is a consulting physicist there. Nissi has her PhD from Purdue and was the director of radiation physics at the Stanford Research Linear Accelerator. She has many years of experience in shielding design and has designed the shielding for a large number of proton therapy facilities and has written extensively on proton therapy shielding. Those of you who are involved in proton therapy may be familiar with the Proton Therapy Collaborative Oncology Group, or PTCOG. Nissi is very involved there and chaired the group that wrote a report on shielding and radiation safety for particle therapy facilities, and was a consultant for the NCRP report that is the most current US report on shielding design. And like Dr. Langen, Dr. Ibbott has given numerous talks at international as well as national meetings and educational programs. So we're very pleased to have both of these well-qualified speakers with us today. And so we will go right ahead with Dr. Langen's talk, and I will hand over to Dr. Langen to share her PowerPoint.
Okay, good morning, everybody from Atlanta. Jeff, is my screen sharing correctly?
Yeah, yes, it is.
Okay. So thank you for the invitation. And in my presentation, I will focus on the regulatory aspects. Okay. Of a proton therapy facility. So we as medical physicists may be tasked with involving ourselves in the regulatory process when it comes to proton therapy. I know it's nobody's favorite, but it still has to be done, and it has to be done correctly. You may be somewhat apprehensive about this process. What I recommend is that you put yourself in the regulator's shoes. Your facility may in fact be the first proton facility that your regulator has ever dealt with. So while there may be some apprehension on your side, please understand that they also may be somewhat apprehensive about this process. So I recommend to reach out to your regulators early and explain yourself well. The sooner you can establish a relationship of mutual trust with your regulators, the better it is, because some of the aspects are not obvious and they need to be discussed with the regulators, and you need to come to some sort of agreement how to handle these. So there are typically 3 steps. The first step is often the submission of a shielding design for approval. I won't talk about this much more because Nissi will really deal with this. The second question you need to ask is, do I need a radioactive material license? And the question, or the answer to this may be yes. Depends a little bit on if you are under a broad scope license or if you're a single facility. So I'll spend a little bit of time talking about this. And then lastly, you may have to register your facility. And part of this is typically a shielding survey. So let me start with a radioactive materials license. Radioactive material at a proton facility is produced incidentally to the operation of the facility. So what you need to apply for is likely a possession and a storage license. Depending on your vendor, the accelerator may be tested at their facility, at the production facility, prior to shipping. In that case, it comes slightly activated, or some activated components come with it. Please keep this in mind because you may have to have the radioactive material license in hand prior to the equipment being shipped. It can take several months for regulators to issue this license, so please process or start this process as early as you can. So radioactive material is produced wherever you lose protons. Where are they lost? That very much depends on your particular facility. I will walk you through an example of what we had to deal with in Maryland, but it may look very different for you. If you have a cyclotron, it's different than if you have a synchrotron, and so on. If you have one room versus many rooms. But anyway, so it's typically produced in the accelerator. Your extraction efficiency is typically not 100%. If you have an energy selection system, there's radioactivity produced in that piece of the component in the beamline. It also is produced in your water phantom and finally in your patient. So I will walk you through an example of how we applied for a radioactive material. And the example is a 5-room cyclotron-based pencil beam scatter facility. In a cyclotron facility, you have an accelerator that produces energies of 250 MeV in this case. Everything that comes out of your cyclotron has this energy. So the very first thing you need to do is to degrade the beam energy to the energy that is needed. This is done by a piece of equipment called the energy selection system. It sits right at the exit of the accelerator. In our case, it's a carbon wedge, and the carbon wedge is followed by energy slits. So this works very well. However, unfortunately, the energy selection system is very, very inefficient. It's really quite surprisingly inefficient. So if you go from 250 to 200 MeV, the transmission through the system is only 10%. And it drops furthermore the more you need to reduce your energy. So if you go to one from 250 to 75 MeV, the transmission efficiency is only 0.2%. So that's 1 of every 500 protons that go into the ESS will make it out, which means 499 are lost in the system. So those lost protons generated a strong secondary neutron field. This needs to be shielded against. Nissi will talk about this. But the lost protons also activate the components of the system. So you are often charged with estimating the amount of activated material, because when you apply for the license, you need to state what you are applying for. So I'll walk you through how we went about doing this. So radioactivity is continuously produced due to beam losses. You're going to produce a mix of short and long life isotopes. Each of these isotopes on its own builds up to what we call the saturation activity. Saturation activity is reached after about 4 to 5 half-lives. So in absolute terms of time, of course, this depends. A long life isotope will take longer to build up than a short one. But typically it takes about 4 to 5 half-lives. We looked at the isotope lists that we would produce in our cyclotron as well as in the energy selection system. The cyclotron is mainly steel and copper. There's some tungsten in there. And the energy selection system consists of a carbon wedge as well as copper slits. And here you can see the half-lives. If you look through the list, you find that cobalt-60 is the isotope with the longest half-life. It's about 5 years. So this saturation activity really builds up over the facility lifetime. Other isotopes have much shorter half-lives, so they build up. Their saturation activity is built up much sooner. So at saturation activity, the decay or activity is equal to the production rate. You can calculate the production rate if you know the proton flux or the protons that are lost. You need to know the cross-section, and you need to know the amount of target atoms. So the first question then, before you can calculate how many protons you lose, is how many protons do you need to treat your patients? And as a reminder, when we treat a patient with protons, we don't treat with single Bragg peaks. We treat what's called a spread out Bragg peak. A spread out Bragg peak consists of protons of different energies that stop at different ranges and have different weights. The highest energy proton forms the distal edge, and that's usually the heaviest weighted peak. and the peaks with lower energy towards the entrance site have lower weight. So once you know this, you can do some back of the envelope calculations about numbers of protons that are needed. So if you, for example, assume you want to treat a 5 centimeter cube that has a distal edge of 15 centimeters to 1 gray, you can look at what energy layers you need. The distal energy layer requires 145 MeV. On the proximal side, it's about 120 MeV. If you then look at these layers, you can deduce how much energy each of these protons is losing in your cube. So for example, the distal layer, when it enters the cube, has a residual range of 5 cm. So it loses about 80 MeV in your tumor. For the proximal layer, they have a very short range, so they lose about 22 MeV in your tumor. If you know the distribution and the relative weights of your Bragg peaks, you can calculate the average energy that's lost per proton. For the 5 centimeter cube, that turns out to be about 66 MeV. I know the cube. If I know the cube, I know the mass of the cube. Then I can very roughly estimate the number of protons that I need. I know the mass of the cube, so I know how many joules I need. And you know these, and you know the average energy per proton, so you can then calculate that you need about, in this case, about 1.2 times 10 to the 10 protons to treat this particular cube to 1 gray. So once you know this, and you know your energy layers, you know the energy layer weight, you can calculate how many protons each energy layer needs. You then need the efficiency, or need to know the efficiency of the energy selection system. So this is typically data you get from the vendor. This is not something you can easily calculate. We got this from the vendor. So I know how many protons I need. I know the efficiency. So now you know how many protons need to enter the energy selection system. Consequently, then you know how many are lost. So this is an exercise you unfortunately need to repeat for each tumor type. It is very different if you treat a prostate versus a head and neck case. So we started off by making conservative estimates, and the conservative estimate in this case is a shallow target. That's because if you have a shallow target, you're requesting a lower energy. Your efficiency of the energy selection system is now reduced, which means you're losing more protons in the system. So the mix of tumor sites has a significant impact on calculating the activity that you estimate for a proton facility. It's about a factor of 10 if you go from a deep-seated prostate to a shallow head and neck case. So there are a lot of assumptions in this process, and this is one of the assumptions that has the biggest impact on the final result. So when we constructed our facility, we assumed we're treating 200 fractions per day, and we also assumed that we're treating half day on Saturday. And this was our case mix: prostates, brain, GYN, head and necks, and so on. Now, over the lifetime of your facility, of course, that mix can change. But when you start, you need to come up with a reasonable assumption that you can justify. So after we did this, and we went through all the separate calculations of activity, we came up with a number of 1.6 times 10 to the 16 protons that were lost in the cyclotron per week, and 1.2 times 10 to the 17 protons that we would lose in the energy selection system. So you can quickly see now the energy selection system is the main harbor of activity in a cyclotron-based facility. In fact, if you have a synchrotron, you don't have this device, and this is one of the advantages of a synchrotron-based facility over a cyclotron. So now we have determined I, the proton loss rate. We used publicly available databases to calculate or to look up thick target cross sections. For our targets, we assumed that the cyclotron was 40% steel, 60% copper. Again, that's an assumption. There's obviously much more in that cyclotron than this, but this is, I think, a reasonable assumption. The energy selection system is your main problem. There is the copper energy slits, and different vendors use different materials. So after doing all of this, you can see the saturation activities that we calculated for different isotopes. This is the last column. We added this up for the cyclotron. It was about a little less than 60 millicuries. I'm sorry, we're still using the old units here. In the energy selection system, the activity was quite a bit higher. It was 125 millicurie. There is some more activity that you introduce by neutron activation of the cyclotron and the concrete. So we summed all of this up, and we ended up applying for a radioactive material license for 200 millicurie for our facility. When you apply for a radioactive material license, you are typically tasked to talk about the decommissioning activities of your facility. And in the US, the regulators ask us to look at long half-life separately. Long half-life is anything more than 120 days. And you're asked to calculate an R value. What the R value is, in this column here, you see a value that's actually the exempt quantity for this particular isotope. So the R value is then simply how many units of this exempt quantity is in my saturation activity. And then you sum all of these up and you get a total R value for your facility. And this determines how you need to deal with commissioning activities. In our particular case, the NRC, or we were in an agreement state, this particular R value meant that we need to put $225,000 in a bank account that is reserved for the decommissioning activity. It cannot be touched, and the regulators make sure it isn't touched once a year. All right, so now we applied for the radioactive material license. It was granted to us. And then the vendor announced that they would send us a UN 2910 package. This is a package of the radioactive components that were in the cyclotron. They take this out and they ship this separately from the cyclotron. And we didn't really know what to expect. They really should have called it a crate, because this is what arrived. It was a big crate of radioactive materials that we then unpacked, of course. If you deal with radioactive materials, you typically need a dedicated storage room. This room needs to have access control. You need to have a running inventory, regular wipe tests, and a quarterly inventory. Every quarter we audit the inventory. What is in this room? Well, it's the initial shipment. Most of this, fortunately, goes back into the cyclotron during installation. Any cyclotron parts that comes out of the cyclotron for repair and gets replaced is potentially activated. In general, anything that comes out of the beamline needs to be surveyed. It's sometimes surprising what gets activated. We needed to replace light bulbs near the degrader because they burned out. To our surprise, we found that they became activated. So you then need to inventory this, survey it, and once it decays back to background, you can discard these pieces. But not everything decays, obviously, back to background. So let me move on to facility registration. In our case, we discussed this at length with the state, how to go about this. We ended up registering the cyclotron with the state because that's your radiation source. We then registered each treatment room separately. So we had 5 treatment rooms. When you start a proton facility that has many rooms, typically you don't have all your rooms available immediately. You may get one room that you can start to commission. You can start clinical operations in this room while the vendor gets the other rooms ready. So it may take up to a year until you have all your rooms. That means you really need to do your shielding facility survey in steps. So the first shielding survey was the beamline and the area around the energy degrader. And then we separately did shielding surveys for each room. Again, this really needs to be discussed with the regulator. That is not the way we normally go about this. And furthermore, it is really not obvious when to do this shielding survey. For a LIDAC, everybody is familiar with this. The moment you turn it on, that's pretty much the next thing you do. At a proton facility, there really is no on. There is no switch that you turn on when you have beam. So to just give you a little bit of an example timeline. So the first they may turn on the cyclotron RF, right? Then the first beam is extracted maybe weeks later. Then they commission the energy selection system. They transfer beam into the first room, and then they commission this room. So when is it on? It really is not obvious. So you need to go to your regulators and come to an agreement on how to deal with this. So what we did, we promised to do shielding surveys at each of these milestones that I just mentioned, and we promised to document the results. Then we agreed on with the regulators that we only would do a full room survey once we had full current into the room. And this is the survey that then the regulators wanted to attend. They wanted to be on site for this. And this is what we submitted to the state. This is a slide that shows you the neutron spectrum at different areas in your facility. The thin line is what you get beyond your shielding. So at this point, you really have a very high energy neutron spectrum, which determines the instruments that you need to use for the shielding survey. So we purchased a Wendy 2 survey instrument. It has an energy range from thermal up to 5 GeV. Conventional handheld RAM meters, their response drops much earlier. So we purchased this particular instrument for our neutron surveys. For gamma surveys, we use conventional ion chambers and use them for shielding surveys. When we did the shielding survey, we ran a lot of current into the room, more than what is normally done during treatment. We ran 800 nanoamps into the degrader. We had a water phantom at isocenter, and we used the highest energy. We pointed the gantry to all 4 cardinal angles to survey the respective areas outside the shielding. For the shielding report, then we scaled everything down to 2 nanoamps, which is more typical for treatment. We made some assumptions about beam on time, number of treatments per hour, and so on. And we used those assumptions for our shielding report. The report turned out that we were within regulatory limits. Activation of material, anything that's taken out from the cyclotron/beam line is potentially activated, but in the room you also activate different components. So during your commissioning and shielding survey, you run a lot of current into water phantoms. That water gets activated. Luckily, it really decays quickly, but you need to be aware of it when you're working around it. During treatments, there is a component called a range shifter that is put into a position between the beam exit and your patient. So that also gets activated some. So we wanted to make sure our radiation therapists didn't pick up any extremity dose. So we issued ring badges to our therapy team, and it turns out we stopped doing this at some point because we did not get any readings on them. So finally, I want to take a moment to talk about personnel doses. Of course, you need a badge that both sees photons as well as neutrons. In this case, we have OSLDs. They measure your photon dose, and we use dosimeters that also have CR39 components that measure the neutron dose. Lastly, this is my last slide. Hopefully I've convinced you that being in charge of radiation safety at a proton therapy facility does not need to be so scary. It is initially a bigger job when you first start this route. There's a lot of paperwork to do, a lot of regulators to talk to make sure everything is okay. But once it's in order, it is really not that much of a program to take care of, and it's not that scary. So with this, I want to turn over the presentation to Nissi, and I'm going to stop to share my screen right now. Okay, Nissi?
So greetings to all of you from the Golden State. And now we look more golden than we were before. So here's an outline of the topics that I am going to discuss today. There are currently over 107 operating proton therapy centers worldwide, with another 40 under construction. Some of these facilities are single room like the Madan S250, while others are multi-room. Some facilities are synchrotron based, while others are cyclotron based. So let's consider this cyclotron based facility. The 230 MeV proton beam undergoes energy degradation, and it's then transported through the beam transport corridor to the treatment rooms. The treatment rooms can either be fixed or gantry rooms. Typically, these rooms have mazes which have no shielding at the exit. As the beam is transported from the accelerator to the treatment room, beam losses occur at various locations, which results in the production of secondary radiation. Thus, these facilities require shielding. So secondary radiation is produced by the interaction of protons with any target material in its path, and it's produced during beam losses which occur either in the synchrotron and cyclotron, during the injection process, acceleration and extraction, during energy degradation in the cyclotron as the beam is transported to the treatment rooms, in the various passive scattering systems, in beam shaping devices that are placed near the patient, and in the patient or dosimetric phantom. And the production is going to depend on the proton energy and the number of incident protons, the target material, its composition, density, and dimensions. Now, secondary radiation is comprised of both prompt radiation and residual radiation. Prompt radiation remains on only when the beam is on, and it requires large concrete shielding thicknesses of the order of 0.5 meter to 5 meters, and this results in secondary dose to the patient. But the residual radiation remains even after the beam is off, and this can result in external and internal radiation exposure from activation, and so it may require mitigating measures like localized shielding, increased ventilation, and administrative procedures. So the effective shielding design requires understanding of physics behind secondary radiation production. So proton interactions above 50 MeV will result in the production of an intranuclear cascade. And similar to a water cascade, there is a succession of stages in the intranuclear cascade. And this cascade is very important in the shielding design for protons. So here's a qualitative description of the intranuclear cascade. An incoming particle, such as a proton or neutron, will interact with individual nucleons in the nucleus, producing a spray of particles. Now, the scattered and recoiling nucleons will proceed through the nucleus, and each nucleon may interact with another nucleon, leading to the development of a cascade. Now, some of these nucleons may escape the nucleus, but a very large fraction of energy is transferred to a single nucleon, and this nucleon with energy greater than 150 MeV is forward peak, and it will propagate the cascade. The nucleons with energies between 20 and 150 MeV will transfer their energy by nuclear interactions to several nucleons. So on an average, each nucleon may receive about 10 MeV. The charged particles will be quickly stopped by ionization, and neutrons will predominate at the low energies. Now, the energy of the nucleons that do not escape the nucleus will be distributed among the remaining nucleons, and the original nucleus will be left in an excited state. It will then de-excite by emitting evaporation nucleons, that's neutrons or protons, and then alpha particles and fragments. These low energy charged particles will deposit their energy locally, and the evaporation nucleons are emitted isotropically. That's the same in all directions. The energy of these neutrons extends to about 8 MeV, and so these neutrons travel long distances continuously depositing their energy. The remaining excitation energy will be then emitted as gammas, and the de-excited nucleus may be radioactive. So now when we talk about targets, we refer to thin and thick targets. Thick targets have ranges have thicknesses which are much greater than the proton range, and the protons are completely stopped in the target, and therefore the neutron spectrum that's produced is much softer in the forward direction when compared to a thin target. So the use of thick targets in shielding calculation is not conservative, especially in the forward direction, as I will describe later. Now, thin targets have thicknesses which are much less than the proton range, and the protons lose an insignificant amount of energy in the target. So the full incident proton energy is available for neutron production, and this produces a harder neutron spectrum in the forward direction. So here we see the effect of target dimensions on dose for 250 MeV protons incident on a graphite degrader, and this is in the forward direction 0 to 10 degrees. And I use the word dose loosely to refer to effective dose. So if we look at the data, we see that the dose for the 2.5 centimeter graphite is much higher than the dose for the 25 centimeter thick target. So the thin targets are producing a higher dose. Now the neutron yield is defined as the number of neutrons produced per proton, and it's going to depend on the proton energy, the target material, and its dimensions. So here we see the neutron yields from thick targets, and the thick target neutron yield is proportional to the square of the proton energy between 50 MeV and 500 MeV, and it increases with mass number at these higher energies. The thin target yield, however, is proportional to the target thickness. So above 50 MeV, these neutrons that are produced are increasingly forward peaked. And for shielding calculations then, it's really the angular distribution of the particle yield and the angular and energy dependence of the particle spectra that are more important than the total yield. So here we see the angular dose profile for a thick tissue target for various proton energies. So as the energy increases, the dose increases because the thresholds for nuclear interactions are exceeded. And as the production angle increases, the dose decreases and subsequently levels off. Thus, you will need more shielding in the forward direction. Now, neutrons can be classified according to their energy as follows. Thermal neutrons have an average energy of 0.025 electron volts and typically less than half an eV. Intermediate energy neutrons have energy between half an MeV and 10 keV, fast neutrons between 10 keV and 20 keV, and they include the evaporation neutrons that I discussed. The relativistic neutrons have energies greater than 20 MeV, and they include cascade neutrons. So it's important to remember that for neutron energies below 20 MeV, nearly all the neutron interactions are elastic or inelastic scatters, and absorption is really only important at thermal energies and at a few resonances in the intermediate energy range. Now, thermal neutrons, they only gain and lose small amount of energies through elastic scatter. They will diffuse about and eventually get captured by the nucleus. And this capture cross-section for neutron energies less than 1 keV decreases with increasing energy. Now, this excited nucleus will then de-excite and it will emit capture gamma rays. The energy of the capture gamma rays from hydrogen is 2.22 MeV, whereas from boron, it's only 0.478 MeV. And further, the boron capture cross-section is 10,000 times higher than the hydrogen cross-section. So if we are shielding for a maze door or any ducts that are penetrating above the door, we typically would use borated polyethylene and lead. Now, fast neutrons also undergo elastic scatter. Both the kinetic energy and the momentum are conserved, and the fast neutrons become thermal neutrons by elastic scatter. So the interaction with hydrogen is like a billiard ball collision because the hydrogen has the same mass as the neutron. So a neutron can transfer its entire energy in a head-on collision to the hydrogen. And this is really the primary process of energy loss below 1 MeV in hydrogenous materials such as concrete, polyethylene, etc. And it's also the dominant interaction below 10 MeV for all materials. Now, fast neutrons also undergo inelastic scatter. Here, the kinetic energy is not conserved, but the nucleus absorbs some energy. It's left in an excited state. It then de-excites and emits inelastic gamma rays. And this typically will occur above the lowest inelastic energy level in the material. And for instance, in iron, that's 847 keV. And this is really the dominant process above 10 MeV for all materials. Now, in high atomic number materials, inelastic scattering will reduce the neutron energy and thus make the hydrogenous material that follows much more effective. So if we use steel shielding, we must always have some hydrogenous material following the steel because steel is transparent to some low energy neutrons, as I will describe later. Now, there are also various neutron capture reactions as shown in this slide. And what's important to remember is that for fast neutrons and intermediate neutrons, scatter is much more likely than capture. Whereas for thermal neutrons, it's the capture that's important. Now, relativistic neutrons, they undergo inelastic interactions, and shown here are the neutron inelastic cross-sections. These cross-sections increase with mass number, and they decrease with increasing energy and reach a constant value roughly above 150 MeV. So this means that the neutrons with energy greater than 150 MeV will control the radiation environment for protons with energy greater than 150 MeV. So shown here is the inelastic cross-section in iron 56, and 92% of steel is iron 56, and iron has a very important shielding deficiency. So the lowest inelastic energy level is 847 keV. Below 847 keV, only elastic scatters occur, and this is a very inefficient process. So there is a buildup of neutrons below 847 keV when you use iron. Further, this is the region where the radiation weighting factor is very high. And also, if one looks at the total neutron cross-section, one sees that there's a minimum at 27.7 keV and 73.9 keV. So you will find large fluxes of neutrons behind steel shielding. So whenever we use steel, we use hydrogenous material. So we could use steel and concrete, and then the water content would be, we would want at least about 2% water content. Now, the attenuation of relativistic neutrons is characterized by an initial buildup of low energy nucleons followed by an exponential attenuation. And the dose can be approximated by an exponential function over a limited range of shielding thickness, where here H is the shielded dose at 1 meter and H0 referred to as the source term is the unshielded dose at 1 meter, and lambda is the attenuation length. The attenuation length increases with neutron energy from 20 MeV to a few hundred MeV, and it depends on the neutron energy, the production angle, the composition and density of the shielding material. It also changes with depth as the spectrum changes and eventually reaches an equilibrium value. So what are the characteristics of a shielded neutron field? Well, the relativistic neutrons will continuously propagate the cascade, and they will regenerate low energy neutrons and charged particles in the shield at all depths via inelastic reaction. And the yield of the low energy neutrons will increase with increasing proton energy, but these low energy neutrons have much higher cross sections. So eventually, the radiation field will reach some equilibrium condition beyond a few mean paths. So deep within the shield, neutrons with energy greater than 150 MeV will regenerate the cascade, and even though they are few in number, and they will be accompanied by numerous low energy neutrons. So a typical neutron spectrum observed outside a thick shield consists of peaks at about 2 MeV, which are called the evaporation peaks, and at about 100 MeV, and Katja showed that in one of her slides. So how do we do calculations for shielding? Well, there are many Monte Carlo codes available, and FLUCA and MCNP are two of the well benchmarked and widely used codes. You can do a full computer simulation modeling the entire room, geometry, target, and all the other details. And we typically would use site-specific composition and density of the shielding materials and the targets. Then we would calculate the total dose from all particles. And Monte Carlo should be used for maze and penetration scatter calculation because analytical methods are very unreliable. Now, full Monte Carlo simulations for a specific room design are time consuming, and they're not very cost effective because the layout undergoes numerous iterations during the design phase. Now, people have used analytical methods in the past, and these are basically line of sight models. They assume a point source. So we see a schematic here. Here, the dose outside the shielding is given by this expression, where H0 is the dose at 1 meter from the source, R is the distance to the point of interest, and D is the slant thickness of the shielding, lambda is the attenuation length, and this is the production angle theta. Unfortunately, these methods are just limited to transverse shielding and simple geometries, and they do not consider the production angle, the target material, the density, the dimensions, the shielding material, its composition, etc., etc. So they are not recommended for use. So that leaves us with the hybrid approach. This is a combination of Monte Carlo and analytical methods, and we can actually derive site-specific source terms and attenuation lengths that are independent of geometry using Monte Carlo. And we consider various site-specific parameters like the particle energy, the production angle, the beam size, the target material, dimensions, density, shielding material, its composition, density, etc. And these are particularly useful during the design phase because, as I mentioned, the facility layout will undergo several iterations, and they are much faster than Monte Carlo calculations. However, a word of caution. Published source terms and attenuation lengths should not be used because they typically assume thick targets and they are available only for a limited number of materials. And they also assume theoretical concrete composition and density when we should be specifically using the site-specific concrete composition and density. So this is the expression that we would use for the hybrid approach. And here we see that the source term is a function of the proton energy and the production angle, and the attenuation length is a function of the production angle. So we will use Monte Carlo methods to derive the source term and the attenuation length. And how do we do that? Well, a pencil beam of protons is allowed to strike a target, which is placed at the center of spherical concrete shells. These shells are then divided into polar sectors, and the volume average fluence is scored in each element. And this is then converted to dose using fluence to dose conversion factors. So we then plot this data and note that the y-axis is logarithmic and the x-axis is linear. So a straight line on a semi-log plot indicates exponential attenuation. So we see that first there is a dose buildup up to maybe about 60 centimeters, and then we have an exponential decrease. So we can actually fit this data to a source term and an attenuation length, and we do that over here. And we will get a source term of 0.0166 picosievert at 1 meter per proton, and an attenuation length of 52.6 centimeters for this concrete. That corresponds to a half value of 36.5 centimeters. So once we have this information and we know the total number of protons per year at each treatment energy from the workload, we use the drawings to get the distances. We can actually calculate the dose. So what are the shielding design considerations? Well, we need the workload and the usage, and Katja mentioned some of that. This has to come from the user and the equipment vendor. And for shielding, we need to know the phantom composition, its density, dimensions, the field size that we're using, the annual number of protons delivered at each treatment energy, and for QA. And the beam losses have to be provided by the vendor, and this can be quite complex. Sometimes we need to know where the loss points are and what's the annual number of protons at each treatment energy for each loss point. We need to know the target material, the composition and density and dimensions for each loss point. Then we need architectural drawings from the architect, and these should show plans and sections. All the dimensions should be called out, and we also need to see like where the penetrations are. Then the user needs to provide occupancy factors and area type for adjacent areas. Are these adjacent areas controlled or non-controlled? And finally, we need the concrete, the shielding material, the composition, and the oven dry density. So here I show you the dose attenuation of 3 different concretes. They have the same density, but different compositions. And you can see here, for instance, that 448 centimeters of concrete A will result in the same dose as 405 centimeters of concrete C. So that's about 43 centimeters different. And so that composition plays a big effect, or it has a big impact on these calculations. So finally, let's look at the mazes. How do we design mazes? Well, the radiation at the maze entrance will consist of neutrons that scatter through the maze and neutron capture gamma rays. And the forward directed radiation should never be pointed towards the opening of the maze. The dose at the maze entrance can be reduced by reducing this cross-sectional area A, increasing the maze length R1, and increasing the number of lengths. And typically you would like to have mazes legs perpendicular to each other, so you can obtain at least 2 full scatters to the entrance. So once you've done all the calculation, then you can write a shielding report and submit it to your regulatory agency for approval. So with that, let me conclude. Thank you for your attention.
Thank you, Nissi, and thank both of you for these excellent presentations. You've heard now from Katja about regulatory issues, and from Nissi the details of performing a design of the shielding. Nissi, thank you, very good. And so we've had a number of questions from people, and let me also just point out in the chat that 2 people have suggested some additional references that may be available and may be of interest to many of you. And so that actually leads into the first question, which I think is for Katja, although of course either of you could chime in on these questions. Katja, we mentioned the NCRP report 151 for shielding design. It's commonly used in the US, but what other publications and what other regulations and standards are available elsewhere? What would you recommend that people look for in their own countries?
It's difficult for me to recommend what to do in other countries. Obviously, your respective regulatory papers need to be consulted. We ended up going through a lot of publications that dealt with what particular isotopes are to be expected for generation. And there was really not one single document that we looked at. Unfortunately, there is very little information about the decommissioning of facilities. I saw one thing in the chat room that talked about how do you activate or do you not activate the concrete? Yes, you do activate the concrete. And those are particularly long half-life isotopes. So there is very little information available on this. It really was a combination of literature, resources. Some of them were quite old. Okay, so we found that older publications gave us a good idea of what isotopes to expect, but the regulatory body is different in each country. Here we obviously looked at the Nuclear Regulatory Commission guides. So it's not a good answer to what you were asking, but there is no one piece of, no one source. I did look at the PT Court report that NISI was involved in. That gives some idea of what is, how to go about a calculation of the active isotopes. So this is a report that I would recommend highly as well.
Yes, excellent. International reports like the IAEA document and the PT Code report probably are good sources for people. And you mentioned activation in the concrete shielding. This question came up about that, perhaps for NISI. Should one select a particular type of concrete for shielding?
I'm assuming that the question meant that in order to minimize activation, should we select a particular type of concrete?
Yes.
And the answer to that is no, because what happens with concrete is when you are building a facility, you use concrete and the mix comes from the local quarries. So you want to use all the material that's in your local area. The minute you try to make anything special, the cost will increase because things have to come from outside, outside the area, and that costs a lot of money. So this is why I say we should always use site-specific concrete composition and density. And I don't think the consultant should ever upfront specify what the concrete composition is. And just yesterday, I had a situation in which a certain concrete density was specified, and the contractor told me that it would cost $250,000 more to get that particular type of concrete. And I mean, this is not a minimal cost.
Not at all.
Yes, Jeff, I may just add an anecdote to this.
Please.
We had a lot of visitors that we hosted at one of our proton facilities, and one of those visitors had designed the inside of the cyclotron vault using Norwegian marble. So I thought that was a very interesting. I mean, I didn't ask many details, but I suppose that was exactly because they anticipated that activation then to be less. And as Nisi said, this is something you need to weigh up. I mean, this is obviously not cheap. it reduces your decommissioning costs, but it increases your building costs. So this is something you need to weigh, one versus the other.
Yeah, thank you both for that. We've had other questions about the cost, and of course, cost is going to vary a great deal from one location to another. But your point, both of you, about using local materials to keep the cost down is very important. Nissi, we had a question about the Monte Carlo calculations, and I think someone is wondering who will do those calculations. Is this something that the local facility physicist would be expected to do, or would they hire a consultant to do?
I think if the local facility has the capability to do it and the person who is doing it has shielding experience, that's fine. If not, they should just hire somebody who has the experience and the expertise.
Yeah, and obviously that's something that's going to require very specialized knowledge that not the average clinical medical physicist would have. Let's see, question for either of you. Would you introduce any unique features into your design if the facility was considering using the proton machine for flash radiation therapy?
I think the answer is no. Okay, and I say that because the dose that you deliver for flash is the same, right? You deliver fewer fractals. Clearly, you deliver it faster, but unless your workload is expected to increase significantly, I believe the answer is no. It's going to be a faster delivery, but it also requires particular careful setup. So I think you will probably not treat that much more dose in a given week. But you need to think about that. But unless that increases, I think the answer is no.
Yeah, very good.
I don't know if Nissi has an opinion on this.
No, I was just thinking that from a shielding point of view, when you do use flash, probably the beam losses change. And so, but that should be provided by the equipment vendor. So that might impact how you do your calculations.
Yeah, you do use right now high energy, which would mean the degrader is open, which probably reduces that part of the shielding requirement. But in terms of actual dose in the treatment room, I think it would be quite similar.
Yeah. Well, I want to be cognizant of the time. I know that we try to keep these webinars to 1 hour. There have been a number of other questions. Many of them, I believe, have been answered by the presentations. So I would encourage people to go back to the recordings, and I hope that everyone has enjoyed and appreciated these talks. Madan, back to you.
Thank you, Jeff. Thank you indeed for your organizing the speakers, organizing the event, and for chairing and moderating this session. It's indeed really pleasure that this webinar has gone so well with the both speakers, Dr. Langan and Dr. Ibbott, doing an excellent job. Thanks to both of the speakers. Thanks to all the participants. And also thanks to Magdalena, who has really been great in providing the technical support. I'm just looking for the slide to share for the next webinar, which is on 6th of October. And that webinar is on effective dose. So please mark your calendar for 6th of October for just a minute. Yeah, this is, here it is, 6th Tuesday, so in 2 weeks time. It will be the standard time as we have been having in the previous webinars. Today we had 1 hour delayed because of EP, who is from West Coast, but otherwise we will have the next webinar at the standard 12 noon GMT. with that, I wish to thank all of the participants, all of the speakers again, and for the excellent arrangement made by Magdalena, and have a wonderful time, whether it is good night for some, good afternoon, and good rest of the day. Thank you indeed.
Goodbye.
Bye.
Thank
Bye-bye.
you.